Hey guys, it's Finn. In this video, before I start coding, I need to show you my implementation in a PowerPoint presentation and why I'm doing what I'm doing and what data structure I use for what. So let's go. So let's assume this orange thing is a genome. Each genome has node genes and connection genes. So we will start at the beginning with, let's say we've got a network with 2 input nodes and 1 output node. So we would have 3 nodes labeled from 1 to 3, basically like this. Let's also say we've got a second genome that looks like this. Now, my idea was when coding this, I got a central system that keeps track of all the genomes and connection genes, so and the node genes as well. So we will create a new system that keeps track of everything. Right at the beginning, there are only 3 input, or like the 3 input nodes, but later on we are also going to put in their connection genes and so on. So now how is it going to work? Let's assume that we are in the mutation stage right now, and the first genome wants to create a connection from 1 to 3. If you remember, the input nodes were 1 and 2, and the output node was 3. So we're going from this neon to this neon. And it wants to create a new connection from 1 to 3. The thing is that it cannot simply create a new connection from there to there, because it must check if there already exists any type of connection like this in any other genome. So how are we going to do this? The idea is that if it wants to create a new connection from 1 to 3, it asks, this is by the way the need class that we already created, it asks the need class to create a connection from 1 to 3. So he will think about, okay, do we got a connection from 1 to 3, or do we create a new one? So he will see that there's no connection, and he will create a new connection from 1 to 3. This in return can be returned, and we have a new connection from 1 to 3, and this should look something like this. Now, let's assume that the second genome wants to mutate a connection from 1 to 3 as well. Now, we're going to do everything again, so it will think, okay, we need a connection from 1 to 3. He will ask the need class. The need class will think about it, and he will figure out that, oh yeah, we already got this connection from 1 to 3. So instead of creating a new connection, he will simply return this this connection from 1 to 3 with the same innovation number. This will ensure that if we have a connection from 1 to 3 in 2 different genomes, the innovation number 1 and 1 is always going to be the same. And this is very important because that's basically how Neat is going to work. If this would not be the case, Neat wouldn't work. So that's basically the idea of connections. There's a different type of mutation where you take a connection, split it into 2 connections, and put a node in between. Now, I thought about this for a while, and in theory, let's say this one does a mutation at this connection, and this one does the same. The nodes in between could have the same innovation number, and the connections as well. I thought about this, and I found a few cases where this would not work. So we will stick that with, if a new connection is created, let's go back for a second. If a new connection is created, we're always going to have a new innovation number. When a node is created, there's always going to be a new innovation number. There's no checking whatsoever. There's always a new innovation number. So let's play this through. If we split this connection into 2 connections and create a new node, this connection cannot be used anymore because this connection goes from 1 to 3. So the first thing is remove this, place a new node in between, and place 2 new connections. So for there basically needs to be more node checking, but we will do this in Java because it's simpler to implement that. So we are going to have a new node with the index 4, and we are going to have 2 new connections from 1 to 4 and from 4 to 3. Remember, this is input. This is node 1, 2, 3, and the hidden nodes are going to have the rest of innovation numbers. Let's say 4. You can see that the Neat system would keep track of all the nodes that have been created. So even though these connections can never be created by any other node or any other genome, we are still keeping track of them to not be confused about that. Now, the last thing is we need to go back for a second into the first video. And when we had the mutation, we aligned the connection genes, and you could see that we aligned the connection genes by taking their innovation number. So the very important thing here is you can see that the innovation numbers are the same when they are lined up, but the type might not be the same. So one could be enabled and the other one could be disabled. This is very important. So also the weights could be different. Let's say we could have a weight of 1 and here a weight of 0, and we might still have the same innovation number. So how can we achieve this in Java? It's very important to note that these connections are not the same object. So how we will do this? We will, each time we access a connection gene or create a new connection gene, we are not actually going to return this object, but we are returning a copy of that. That's basically what I need to tell you. So let's talk about the data structures that we are going to use. For the nodes, we can simply use ArrayList because we don't need to check if it exists or not. We're always creating a new node when we need a new node. But about the connections, so I thought about this for a while, and you might not like my choice, but I think it's the most easiest to understand. So we will use a hash map, and we will map a connection gene to a connection gene. And if you remember correctly, in the last video we implemented the hash function for our connection gene, and it hashes the from node times a factor to the innovation number added with the innovation number of the to node. So this will mean that if we have a connection that goes from one node to another node, it's always going to have the same hash code. So how are we going to use this? This hash function, we can put in any connection node or connection gene from one neon to another neon and can check if that exists. We don't need to know its innovation number. We can then access this connection gene and get the innovation number. So this is basically a template. What we will do is, if you want to look at it visually, we'll create a new connection gene. We will compare the node from and to node, and we will figure out, okay, this node should be it, and then we can set the innovation number back to our new created connection and return that. So this is what I'm going to do later on. So yeah, the second one is for the innovation number. The first one is to check if it exists or not. And in fact, we're going to map the same object to the same object, but it's going to be untouched, so it will stay there for the rest of the for the rest of the lifetime of the code. And we're always going to create new objects. So let's jump right into the code. So the first thing that we are going to do is we are going to create a new hash map, and we are going to map connection genes to connection genes. And we are probably calling this all connections, because every connection that exists in all of our genomes is stored in there. So the second thing that we're going to need is we're going to need probably an array list. We could, instead of using array list, we could use our random hash set. It doesn't really matter. I'm using the random hash set for now. Actually, there's no good reason for using this. So you could as well use simply an array list. There's absolutely no difference in the code later on. So let's create a constructor, and in the construction we need a few things. We need the amount of input nodes, we need the amount of output nodes, and we need to know the amount of genomes that we are going to have. This is going to be called clients later on. We will not yet deal with them. We will only care about our genomes for now, but I will still put it into the constructor, so it's a little bit tedier. So we will also use create a reset method that resets everything, and the constructor is simply going to call the reset method. In the reset method, we are going to remove all the nodes, create the input nodes, and do stuff like that. So the input size is equal to the input size, same for the output size, and we will do the same with the amount of clients. In fact, I didn't create these variables yet, but I will do that very soon. I'm calling the variable max clients because the clients variable will be used later on. So these variables will be created like this. And next we need a few loops to create the input and the output nodes. So if you remember correctly, we had these x and y values. Don't be confused about what I will do there. So it's going to look nice later on when we have a visual representation of our need objects. So we will start with getting a new node, because this is important for creating the input nodes. And this method is basically used for creating a totally new node. We will assign a new innovation number by simply checking how many nodes there are and adding 1 to that. And in this video, I think I forgot to create the size method, or I did make it private. So if you have it set to private, you should probably check that. So what we will do then is we will add this new created node to all our nodes and return that. We will also we can also return the node by getting the ID of that, so the innovation number. We need to check if it's smaller than our size of our nodes. We could also check if it's greater than 0 or greater or equal to 0, but I didn't do that. You can add that if you like. If it's not, we can simply return get node. So this will, let's say we have only 10 nodes, but we want to return the node at index 15. We're going to create a new node, which is simply the get node method. So right now we can implement the for loop to create the input and output nodes. Because this is independent of any genome, they always have to exist. So we will make a loop for the input nodes and the output nodes. We can simply call get node. So we will create a new node and call the get node function. We will set the x value to 0.1. So this is very important. Every single input node is going to have the x value of 0.1, and every output node is going to have the x value of 0.9. This is used for drawing, so all our input nodes are going to be on the left hand side and the output nodes are going to be on the right hand side. But this is also important later on for creating a new connection, because we will only allow connections from one node to another node where the first node has a smaller x value. This way we can avoid recursion. Let's also create a function that creates an empty genome. This is going to be used at the beginning to create the initial genomes. Basically, this creates a new genome with the input nodes and output nodes, but no connections. So for this, we will create a new genome, and we need to set the need value. It's going to be this, and we will iterate through our input and output nodes. We don't need 2 different loops because our genomes are stacked at the beginning, basically. Like our input nodes and output nodes are at the first input plus output nodes. So we can just iterate through them and add the node to our genome and then eventually return the genome. We also need functions for the connections, and this is a little bit more complicated. First, I want to create a new main method, create a new need object, set the input output size and the clients, but the clients isn't used for now, so you could put any value in there, and we'll create a new genome and check if everything worked, I think. So it's need.get genome or empty genome, and we will print out the amount of connections or nodes in there, I believe. So g.get nodes.size. If we run this, this should hopefully be 6, because we got 3 input nodes and 3 output nodes. So everything seems to be correct for now. Next, I'm going to create the connection gene method to get a connection. We will start with creating a new connection from one node to a different node. So I already explained how I'm going to do this. The first part is creating a new connection from node 1 to node B, and this is also eventually going to be returned. The checking part is to assign the innovation number. Either we already have this connection gene, so we can check in the hash map if it exists, and assign that innovation number. Otherwise, we have to assign a new innovation number. So if all our connections contains the key of this connection gene, which uses the hash function that we already implemented, we are going to set the innovation number to this new connection gene. And I think I forgot that it extends our gene. So it didn't have a innovation number yet, so it has it now. Set an innovation number to the connection gene that we just access in our hash map. So all connections.get of our new created gene, and get that innovation number. This looks a little bit complicated, but if you go through this very slowly, you will probably understand this. And we will otherwise we are going to assign a new innovation number to that. We are also going to have a method to simply copy a connection gene. So this can be static, and actually this doesn't need to be in there. You can also do it manually, but I think this is like a little bit more structured. So this is simply for, it's called get connection, but we are doing nothing but copying this connection. We need to take care of the wakes and the enabled state for this, and this is basically going to be used when we do the crossover thing, because the child is going to have the same weight as either of the parents. So it's also going to have the same weight as one of the parents for each connection. I forgot that when we create a new connection and assign a new innovation number, we also need to add it to all our connections, which is pretty important. This was basically it for this video. I hope you liked it. Tell me what you think about it in the comments, and I hope to see you in the next video.